My project is on double diffusive convection. Sometimes it's called doubly diffusive convection. It depends on the person. I study this phenomenon from a mathematical perspective in my research, but for class, I'm going to present the underlying science and perform a demonstration for you guys. Before I show you the demonstration, I'm going to give you a little background about what double diffusive convection actually is. It's an instability that occurs in fluids where the density is controlled by two components that diffuse at different rates. The easiest way to think about this is in terms of salty warm water and cool fresh water, where the temperature is the quickly diffusing component and the salinity is the slowly diffusing component. In fact, in the ocean, temperature diffuses almost 100 times faster than salt. There are two types of double diffusive convection: diffusive convection, sometimes called oscillatory double diffusive convection, and salt fingering. In diffusive convection, this is the picture on the left, both salinity and temperature have negative gradients, so from bottom to top you get less salty as you go up and cooler as you go up as well. So if you displace a particle down into the warm salty water, since temperature diffuses faster than salt, it reaches thermal equilibrium with its surroundings without picking up much salinity. So this makes it less dense than the surroundings and it'll shoot up, but it's going to overshoot its original location where it then cools down, and then it has a little bit of salinity to it, so now it's more dense and it's going to sink, and this process is going to continue, leading to an oscillation of growing amplitude. In SaltFingers, in the picture on the right, both temperature and salinity have vertical positive gradients, so from bottom to top both heat and salinity increase, and without diffusive effects, a particle displaced vertically downward would be more buoyant than its surroundings and rise. However, when the temperature diffuses much faster than the salinity, the particle cools down while still remaining salty, which makes it less buoyant, so it's more dense, and it starts to sink under gravity. This leads to salt finger looking structures, which is where it gets its name, and the second case is what I do my research on and what I will be demonstrating. For time reasons, I'm not going to go through all of this in depth, but I just wanted to show you that the equations used to model the salt fingering are the incompressible Navier-Stokes equations that we've seen in class. The only difference is that equation 1c is an equation for salinity in addition to our temperature equation, as well as there's a salinity component in the momentum equation. Consequently, a lot of these non-dimensional parameters we have seen before. However, for example, the Rayleigh number is actually a Rayleigh ratio of the Rayleigh number of salinity to the Rayleigh number of temperature, and tau is again a ratio of the diffusivity of salinity to temperature instead of just having one. So now we're at the fun part. This is the demonstration. The blue is warm salty water that just has a blue food coloring dye in it, and I released it with the help of my dad into the cool fresh water. And then if you let it settle for a second, we're going to start seeing the finger-like structures forming. So we displaced the warm salty water into the cool water, and the displaced particles are going to become cooler but keep their salinity, so now they're more dense, and we can see that they're starting to fall. And this video is at 4 times normal speed, so it takes a little bit longer than this. So this video is at 8 times normal speed. I just wanted to give you another view of the finger-like structures that occur as the particles start falling to the bottom, which is again why they're called salt fingers. So then I'm going to conclude this project with a numerical simulation using Daedalus with Prandtl number 7, Rayleigh number 1.1, diffusivity ratio equals 1/3. And this is just a slice in the XZ plane, and you can see the finger behavior. And that's the end of my presentation. Thank you. Cheers.